Evet, sormak istediğiniz bir şey yoksa dersimize başlayalım. Okay, so today I want to solve some problems on chapter 4, right? So that's what I said yesterday, chapter 4. Okay, so the main topic of chapter 4 was to introduce you this notion of vector spaces. Okay, so vector spaces are basically some sets with two operations. One is vector addition and the other is scalar multiplication. So we have seen several examples of this structure. For example, the usual vectors with the usual vector addition and scalar product is a vector space. And there are other examples like the vector space of matrices, vector space of polynomials, vector space of functions. Like there are many other examples. Okay, and then there was this notion of subspace. Okay, so given a vector space, the question is whether a given subset of a vector space is itself a vector space or not. So in this case, when we're checking whether given subset is a subspace, the problem really simplifies because we have to check only two things. The first one is, so we want the sum of any elements in that subset, any two elements in that subset to remain in that subset. Okay, that's the first condition. And the second condition was the scalar product of a vector with any scalar still lies in that set. Okay, those are the two conditions. So here the example is from M22. So if you remember what is M22, so these are matrices, 2 by 2 matrices, right? 2 by 2 matrices. Okay, so here W is a subset of 2 by 2 matrices. So W is a set of all matrices of this form with this condition: A plus B plus C plus D equals 0. And the question is this set a subspace? So what we really need to check is two conditions, as I said. First one is if A and B are two elements from W, then what we want is their sum to lie in W, okay? So this is a question mark. So what we need to show is take any two such elements, A1, B1, C1, D1, and A2, B2, C2, D2. And if we add them, what do we get? We get A1 plus A2, B1 plus B2, and D1 plus D2. Okay, so this lies in W and this matrix lies in W. What does it mean? It means A1 plus B1 plus C1 plus D1 is 0, and A2 plus B2 plus C2 plus D2 is 0. So the question is what? The question is this: whether the sum of all entries here are also 0, right? That's the question. So if I add A1, A2, B1, B2, C1, C2 plus D1, D2, is this 0? Well, yes, because it's basically this plus this, right? So it must make 0. So the first condition is satisfied. The first condition of being a subspace is satisfied. Now, what is the second condition? Second condition says this: take any scalar number, okay? So for us, scalars are real numbers. We show them with the symbol R. And let's take A, B, C, D, their sum to be 0. So the question is this: is this product also in W? So what does this mean? This means Ka, Kb, Kc, Kd. So is this in W? That's the question. This is the question. So this lies in W means what? So the only condition for being in W is the sum of these entries being 0, okay? If they add up to 0, then it's in W. If not, then it's not in W. So for this one, you can easily see that since this condition is satisfied, this condition is also satisfied. So the answer is yes. W is a subspace. Okay. So W is a subspace. Okay, so if we, okay, so any questions here? So if we played with the question, so this number 0 is special. So if we made it 1, what do you think? Is W still a subspace of M22? No. Enes İbrahim Okuren, Barış Hazar says no. And they are right. So is there a simple reason why it is not a subspace? There's one simple reason. Yes, that's true. There is another reason. Simple reason is this space W, in this case, 0 vector, which is the 0 matrix, in this case is not in W, okay? So you can check easily whether a given subspace is whether a given subset is a subspace or not, because the sum of these entries do not make, is not equal to 1, so it's not in W. So 0 vector, W doesn't have the 0 vector. So that means W cannot be, so in this case, W cannot be a subspace. Okay. So if 0 was in W, it doesn't mean that it's necessarily a subspace. But if it is not, then it's necessarily not a subspace. Okay. That was the first problem. Okay. Let's look at next problem. So which of the following sets of vectors span R4? What do you think? So do these two vectors span R4? What do you think about it? Yes, Barış Hazar says yes. Any other answers? Fatih Said Duran is also agreeing. Thank you guys for participating. Okay, so we have two answers and both are unfortunately wrong. I'm sorry, guys. Thanks again for participating, but your answers are not correct. So the reason is R4 is basically it's a 4-dimensional space. Okay, which means so it is spanned by at least 4 vectors. Okay, or in other words, you cannot write any 4 numbers just by using these 2 vectors. Okay, You cannot obtain any two numbers by just using these two linear combination of these two vectors. Because by two variables, you cannot obtain all these numbers, right? There is no way. So for this reason, this is no. This one, for this one, the answer is no. And similarly, for this one, the answer is also no, right? Because it is less than 4 vectors. Less than 4 vectors cannot span R4. The reason is R4 is 4-dimensional. We know that. So we need at least 4 vectors. So this is possible and this is possible. Okay, these two are possible. Let's check. Possible means does not mean necessarily it will be, right? C is also no, but oh, okay. Why? It is possible. It may be yes or no. We don't know the answer. So what you do in this case is so you want to find basically what you want to do is find the number of linearly independent vectors here. Okay, so let's call this V1, V2, V3, V4. So if there are less than 4 linearly independent vectors, then this cannot span R4. Okay, so what you do is you write this. You write this, okay? So what happens? What happens when you write it? So you get this one, right? Let me put 0, 0, 0 here. Okay, so what you want to do is bring this matrix into row echelon form, okay? So so how many leading ones do you expect? So there can be at most 4 leading ones. So if there are 4 leading ones, okay? So if there are 4 leading ones, the answer is yes. If there are less than 4 leading ones, the answer is no. Because less than 4 leading ones means, for example, if there are 3 leading ones, there are only 3 linearly independent vectors here. The other 2 vectors can be represented using those 3 vectors. So in this case, the span of these 5 vectors will be 3-dimensional. Okay, so for this one, I'm not gonna do this row echelon form computation. Okay, I leave it for you to check. And there are also like a lot of online tools that you can use to check whether these are like that brings this into row echelon form. Okay, so you can use those tools as well. Okay, so the same for here. So you have to check. Okay, we don't know whether these span are 4 or not. You have to check. For example, for this one, is there an easy way to check it? I don't see. Okay, for this one, for part C, right? For part C, you see V3 and V1 are the same vector. So you can easily get rid of V3 here, okay? So that remains V1, V2, V4, V5. You want to check whether like these okay, so what you want to check is, so if I erase this part, you get a 4x4 matrix here, right? So you can check this also using determinants. So if the determinant of 4x4 matrix is non-zero, then the answer is yes. If the determinant is 0, the answer is no. Okay, so if we didn't erase that column, we couldn't check determinant because we can only compute the determinant of square matrices. Okay, so you only need to check the determinant of this guy. This is an alternative way of checking. Okay, any questions, guys? Same for this one. So one way of checking whether they span is write these vectors as a matrix and find its determinant. So there are two cases. Either this is 0 or this is non-zero. If this is non-zero, the answer is yes. So these vectors are linearly independent. If not, the answer is no. That's it. Let me know if you have any questions here. Okay, no. So, okay, let's look at another question. It says, show that if these two vectors, the set of these two vectors is linearly independent, and V3 does not belong to span of these two vectors, then these three vectors, the set of these three vectors is also linearly independent. Okay, so let's think about it. So what are we trying to show? We are trying to show that these three vectors are linearly independent. What does it mean? It means if I write this linear combination, I want to check whether only solution is C1 equals C2 equals C3 equals 0. That is the only, we're checking if the only solution is the trivial solution or not. If the only solution is a trivial solution, then these three vectors are linearly independent. If not, then they are linearly dependent. Okay, so suppose C1, C2, C3 be a solution of this equation, okay? Let C1, C2, C3 satisfy this equation. So that means there are two cases. Either C3 is 0 or C3 is not 0. There are two possibilities. If C3 is 0, this means C1v1 plus C2v2 equals 0, right? If C3 is 0, if this guy is 0, then this sum must be 0. But let's see. What did we assume? We assumed that these two vectors are linearly independent. So what does it mean? It means that for this linear combination, the only possible solution is C1 equals C2 equals 0, okay? Why? Because V1, V2 are linearly independent. That's the reason. So if we assume that C3 is 0, then C1 and C2 must also be 0. Okay. Now let's check the other case. If C3 is not 0, what happens? If C3 is not 0, then what happens? So this means V3 can be written. So I can solve this equation for V3, right? How? Because I can write this as minus C1 over C3 V1 minus C2 over C3 V2. Why I can do this? Because C3 is not 0. Then that means I can divide by C3. Okay. Okay, what does this show us? This shows us that basically V3 is a linear combination of this V1 vector and V2 vector. So, which means V3 is in the span of these two vectors. Because I can use these two vectors to represent V3. But this is something that we assume to be not true at the beginning, right? Because we don't want V3 to be in the span of V1 and V2. So this is not possible. Not possible by assumption. Okay, then that means there's only one solution. C3 is 0 and C1 and C2 is 0. So the only solution is the trivial solution. The only solution of this equation is C1 equals C3 equals C3 equals 0. That means the vectors are linearly independent. Okay, so yeah. So what this is saying is, so if you have two vectors, okay, and so you have a plane here, right? So these two vectors form a plane, and if you choose another vector which does not lie on this plane, okay, something like this, then this means these three vectors are linearly independent. Okay, so that's what it's saying. Any questions, guys? Any questions? No? Okay, let's look at this one. Okay, for what values of C are the vectors, this vector, and this vector in R3 are linearly dependent? Okay, so to be linearly dependent, we have to again look at this equation. Okay, so to be linearly dependent means this equation has a solution for C1, C2, C3, which are not all zeros. Okay, so I can write this equation as what? So this means this means like these equations, right? Minus C1 plus 2C2 plus C3 equals 0. And we have two more equations here, which I can represent in this form. Minus 1, 2, 1. And the second line will be 0, 1, 1. And the third line will be minus 1, 2, and C. Okay, so we are looking at this equation. Now, what are we gonna do? We are gonna find the condition that this system has a non-trivial solution. So to do that, we have to bring this matrix into row echelon form. How do I do that? Well, first of all, I can use this operation, minus row 1 plus row 3 to row 3. This becomes 0, this becomes 0, and this becomes minus C minus 1, right? Okay, now let us see. What does this mean? So, okay, so if either this guy is 0 or this guy is non-zero. If this is non-zero, so let's say it is 9. What does this mean? If this is 9, then 9 times C3 equals 0 means C3 must be 0. If C3 is 0, C2 plus C3 equals 0 means C2 is 0. If C2 and C3 are 0, then this means the first line means C1 is 0. Okay, so if this is not 0, then C1, C2, C3 equals 0 is the only solution. Okay, so if C minus 1 is not 0, only solution is the trivial solution. Okay, what is the trivial solution? C1 equals C2 equals C3 equals 0. And the other case is if C1 is 0, if this guy is 0, then this equation will have infinitely many solutions. So infinitely many solutions means there will be non-trivial solutions as well. So in this case, there will be infinitely many solutions, and the system will be linearly dependent. So if C is 1, then linearly dependent. If C is not 1, then linearly independent. These are the only two cases. Okay. An alternative way was to check the determinant of this guy. If the determinant is 0, then there will be infinitely many solutions, and the system will be linearly dependent. If the determinant is non-zero, then there will be only a unique solution, which is 0, 0, 0. That's it. Any questions, guys? Kalem gerçekten güzel yazıyor arkadaşlar. Tablette falan yazan var mı aranızda? Tablette yazı yazan yok galiba. Okay. İkinci nesil mi? Yok ya, bu bilmiyorum, bu iPencil diye bir şey. Apple değil yani. Ama iPad Apple kalem muamelesi yaptı buna bir şekilde. Yani baskı, yani pressure özelliğinin olması lazım değil mi? Böyle bir şeyimiz yok şu anda. Pressure derken yani böyle bastırınca daha farklı olması gerekiyor galiba. Yanında yedek uç vermediler mi hocam öncekinde? Önceki çok dandikti ya. 10 liralık kalemdi o. Uç falan vermediler onda. Bunun ucu var ama. Bunun ucu yumuşak değil. Biraz sert böyle. Ama basınca karşı herhalde iPad'in özelliği değil mi? iPad'in özelliğinin olması gerekiyor sanıyorum. Benim iPad'imde basınca karşı bir şey yok. Okay, let's continue. In exercises 19 and 20, find the basis for the given subspaces of R3 and R4. Okay, so let's do just some of them. Let's look at this last one, okay? So the question is find the basis. for this subspace. So the subspace of all vectors of this form. Let's find about subspace. So how do we do? What we do is we write this vector. We write this vector in terms of, so separate A's, separate B's, and separate C's. And then write A times 1, 1, 0, minus 1, B times 0, minus 1, 1, 1, plus C times 1, 0, 1, 0. So all the vectors in this form can be written as a linear combination of these three vectors. Okay, so which means, so if we call this space the W, then W is basically span of these vectors, right? Now the question is whether, so to be a basis, we need two things. They have to, so given subspace must be spanned by these vectors. And the second thing is these vectors must be linearly independent. So the second question is, are these vectors linearly independent? Okay, how do we check it? Again, what we do is we write these vectors as in this form. And then, so we can write zeros here, doesn't matter. And then we try to bring this into a row echelon form. And in the row echelon form, it will give us whether we have 3 leading ones or less than 3 leading ones. Okay. So if we do that, what do we get? So how do we take this into row echelon form? So we use these operations, minus row 1 plus row 2 to row 2, and row 1 plus row 4 to row 4. That will give us 1, 0, 1. 0 minus 1 minus 1, right? 0 and 0, 1, 1. And this is 0, 1, 1. Okay, now we can use the second line to make the other lines equal to 0. So if we do this, what do we get? We get 1, 0, 0, 0. 0 minus 1, 0, 0. 0 minus 1, 0, 0. Okay, so these two are in the same line. We have this. Okay, so we can also write this in this form: 1, 0, 0, 0, 1, 1, 0, 0, 0, 0, 0, 0. Okay, what does this mean? This means we have only 2 leading ones, right? So these are the only leading ones. So we have, how many vectors do we have here? We have only, so basically we need only 2 of these vectors, which means the second vector is a linear combination of the third vector, right? So we only need the 2 of these vectors. So So v1 and v2 also span the same vector, right? So let me write this way. So it turns out that we don't really need 3 of these vectors. Okay, so here you see these 3 vectors span W, but we can see that the third one is basically a linear combination of the first 2, right? If I add these 2 vectors, I get 1, 0, 1, and 0. So third vector is really redundant here. So third vector shouldn't be in the basis, because to be a basis, these vectors must be linearly independent. Okay, so we can ignore the third one, and we see that from here because only the first and the second columns have leading ones, which means vector 1 and vector 2 are linearly independent, but the third one is depending on the first 2. Okay, so basis for W is these 2 vectors. Okay, this is an interesting example because at a first glance, it looks like we have to choose all these vectors as in the basis, but actually no, because the third one is depending on the first 2. So we have to ignore the third one, okay? That's the result. Any questions here? Okay, I think we have, so this is the last example I chose. What is it asking? So it's saying that in exercises 7, 8, determine which of the given subsets form a basis for R3. And then express this vector as a linear combination of those vectors. Okay, let's do some inspection. Now, to be a basis for R3, we need exactly 3 vectors to be in the basis. Okay? Because less than 3 vectors cannot span the space, and more than 3 vectors are not linearly independent. But to be a basis, we need both. We need both them, we need both the linear independence and span properties. So this cannot be a basis. For this one, this is no, because it contains 4 vectors. 4 vectors cannot form a basis for R3, okay? What about the others? What do you think about this one, for example? Is this a basis? Okay, let me answer the question. So this cannot be a basis. Because 0 vector, so we have the 0 vector here, and once you have the 0 vector, that set can never be linearly independent. Cannot be linearly independent. Okay, what is the reason for that? Because if you write this, if you write this equation will have always non-trivial solutions, because I can always choose C1 and C2 to be 0 and C3 to be any number I want. I can choose 10, I can choose 95, doesn't matter. So I can choose any number. So this system has always non-trivial solutions. So this has always non-trivial solutions. So you see, you cannot put the zero vector in any basis, okay? So basis vectors must be different than zero. If you see zero, that's not a basis. So we excluded these two so these two cannot be bases. What about the rest? For example, the first one, can it be a basis? So for three vectors, you only need to check whether they are linearly independent or whether they span. Because if they are linearly independent three vectors, for three vectors in R3, they will span. And if they span, they are linearly independent. They are the same thing for three vectors in R3, okay? So one way of doing that is just checking this determinant. So if this determinant is zero, then the answer is no. If the determinant is non-zero, the answer is yes. So how can we find this determinant? Just expand in this column, okay? So this will be -1 to the power, so it is the second row and third column times 1. And I erase this and this to get 1113, which gives me -3 minus 1. So this is non-zero. So the answer is yes. So for this one, the answer is yes. This is a basis, okay? They are linearly independent and they span R3. The same thing for this one, okay? You only need to check the determinant 1, 1, 2, 2, 2, 0, and 3, 4, -1. So I think for these ones, the determinant is also non-zero, right? So we can check this. Let's use the third row. This is 2 times -1, 3 plus 1, 2, 3, 2, 4, and -1, -1 to the power 3 plus 3, 1, 2, 1, 2. Okay, so this part is basically zero. Oops, this is too big. This determinant is zero because the rows are same, right? What about this part? This gives us 2 times 8 minus 6, which is 2 times 2, 4. And this is not zero, okay? So the answer is also yes for this one. Okay, guys, so that's what I wanted to say for as the last class. Next week, we don't have a class. If you have any questions, you can always email me. I sent some textbook exercises yesterday, so you can check those for the midterm exam. I will also send some suggested exercises for the final exam. And that's the end of the semester, okay? So for next year, I will also be teaching Calculus 1 in the first semester and Linear Algebra for the second semester. So you're free to come and sit anytime you like, if you want to. Other than that, everything was fine. Thank you for all attending the classes and not leaving me alone. Okay, thank you. Yeah, that's it. Görüşürüz arkadaşlar. Hepinize başarılar diliyorum. Her zaman uğrayabilirsiniz konuşmak için. Görüşmek üzere. Hepiniz iyi bakın kendinize arkadaşlar.